Okay, today's lesson is on roots and radicals, and this should go in log page 11 of your logbook. Please be sure you put it on your table of contents. Today what we're going to be talking about are roots and radicals. In this section we're going to introduce a new category of expressions and functions that contain roots. For example, the reverse operation or the inverse operation of squaring a number is finding the square root of a number. You need to underline or highlight this sentence. The reverse or the inverse operation of squaring a number is finding the square root of a number. So please be sure that you are highlighting that. This is the symbol that means the principal square root of a number. Okay, this symbol means the principal or the positive square root. The principal square root of a number. And remember that the principal square root is positive. The symbol is called a radical sign. The number under the radical sign is called the radicand. So if I put a number under here, this is called the radicand. Together we refer to the radical sign and its radicand as a radical expression. Okay, here is what we're looking at. Let's move this just a little bit. Okay, the square root looks like this. The radical symbol is this little house type symbol. The radicand is the part underneath the radical symbol, and together they're called the radical expression. Now, we're going to look at some radicals and try to make some sense of what they mean. Okay, some examples. The cube root of 8 is equal to 2. Because 2 cubed is equal to 8. So if I ask you to find the cube root of 8, what I'm asking you is what number raised to the third power is equal to 8, and that number would be 2. Okay, the second one is the cube root of negative 8. It's asking me what number raised to the third power is equal to negative 8. Well, that answer would be negative 2, because negative 2 times negative 2 times negative 2 is equal to negative 8. The fourth root of 81. It's asking me what number raised to the fourth power is equal to 81. Well, that number would be 3, because 3 times 3 times 3 times 3 is 81. The next notation is the opposite of the fourth root of 81. The opposite of the fourth root of 81. That's how you read this symbol, the opposite of the fourth root of 81. Well, if the fourth root of 81, okay, I'm going to cover up this little negative sign. If the fourth root of 81 is 3, then the opposite of 3 is negative 3. So the opposite of the fourth root of 81 is negative 3. The square root of negative 36. This little number right here is called the index. And if we write the number in there, we're going to, like a 3 or a 4 or a 5, then we can see very clearly that the index is 3 in this case. The index is 4 in this case. If it's not written, the index is understood to be 2. No index written means that it's understood to be a square root. Okay, if there's no index written, it's understood to be a square root. Now, when I have a square root of a negative number, this is not a real number. So whenever I see a negative number as the radicand with a square root or a fourth root or a sixth root or an eighth root, okay, an even root, whenever you have a negative number as the radicand of an even root, then you have to say that the answer is not real. You cannot take the square root of a negative number. Okay, think about that and let's see if we can figure out why that's the case. All right, we're going to do some examples now. We're going to evaluate the square root of negative 16. Well, look with me at this. The principal square root of a negative number, negative 16, is not a real number. Later on, you're going to learn about some numbers that are called complex numbers, and you'll learn how to evaluate these. But right now, we're just going to say this is not real. So right now, there is no solution. Let's look at letter B. The square root of 144 plus 25. The square root symbol, that radical, acts like a grouping symbol. And we have to do what's inside the grouping symbol first. So we're going to add these two together first, and we're going to get the square root of 169. And then I'm going to know that the square root of 169 is 13. So the principal square root of 169 is 13. Now remember that the square root acts like a grouping symbol. So in this case, I'm going to do what's under the grouping symbol first. So I'm going to say the square root of 144 plus the square root of 25. Well, what's under the grouping symbol is just the radicand. So I'm going to go ahead and take the square root of 144, which gives me 12. And I'm going to take the square root of 25, which gives me 5. And then I'm going to add those two together to get an answer here of 17. Remember that your square root acts like a grouping symbol, so you have to do what's under the radical first. Do what's under the radical first, then simplify. Okay, now we're going to look at, let me move this up so you can see it a little bit better. Now we're going to look at finding roots. Okay, the first one that we're going to look at is the square root. So if I am simplifying the square root of a squared, remember that the index here is not written, so I understand that this is a square root. So what this means is that underneath my radical, I have a times a. So if the question here is, what do I multiply by itself? What do I square to get a squared? Then the answer would be, I multiply a by itself to get a squared. So that means, I should not put an equal sign here. That should not be an equal sign. Take that out. Okay. The question is, what do I multiply by itself to get a squared? And that would be a. So that means the square root of a squared is just equal to a, because a is the number that I multiply by itself to get a squared. Okay, so let's look at some practice with finding roots. Well, we talked about at the beginning of class today how we recognize our square roots. So I want you to get into the habit of looking for square roots. However, in order for us to simplify this square root of 45p squared, we're probably going to need to make a factor tree. So let's go ahead and make a factor tree for 45. Okay, 45. I know that 5 goes into 45. And I know 5 goes into 45 9 times. Now 5 is prime, so I'm going to circle it. 9 is not prime, so I know that I can factor it down further. So I have 3. 3 is prime times 3. Now I have my prime factors for 45. 45 is 3 times 3 times 5. And I just tend to put these in order from least to greatest. You certainly don't have to, but it might be helpful to you. And p can be rewritten as p times p. Now what we're going to do is we're going to look, since we have an understood square root here. I'm sorry, I put my hand right in your way. Since we have an understood square root here, we're going to be looking for pairs of numbers. So we're going to be looking for pairs, okay, meaning groups of 2. Let's see if I can get this all onto my screen. Let me scooch over just a little bit. Groups of 2, because my index is equal to 2. Okay, so we're going to be looking for groups of 2. Here's a group of 2 3s. Okay, 2 3s under the radical get to come out of the radical as 1 3. So these 2 3s come out of the radical as 1 3. I have a group of 2 p's. 2 p's under the radical get to come out. They come out as 1 p. And the 5 underneath here doesn't have a partner, it's not a pair, so it has to stay under the radical. So that's going to be 3p square root 5. Okay? And that's how you do square roots. Okay, let's look at another example. I'm going to move this over and we're going to do letter B. Okay, let's look at letter B. Letter B looks like this. The square root of 200 m to the 4th n. Okay, so I'm going to come over here and I'm going to do my factor tree. Oh, wait, you can't see. I'm just working away and you can't see. Say 200, the square root of 200 m to the 4th n. So 200, doing our factor tree. Well, I can look at that and say, well, I know that 10 goes into 200, and I know that 10 goes into 220 times. You can do 2 times 100 if you want to. It doesn't matter how you break this down as long as you go all the way down to your prime factors. 10 is 2 times 5, and I know that 2 is a prime factor and 5 is a prime factor. And 20 is 4 times 5. Well, 5 is a prime factor, but 4 is not. 4 is 2 times 2. So 2 now are prime factors. So I'm going to come up here and I'm going to write 200 in prime factorization. So I have 3 2's, 2 times 2 times 2, and I have 2 5's, 5 times 5. Now, I also have m to the 4th power. That means m times m times m times m. That's 4 m's. And then I have 1 n times n. And again, I'm going to look for pairs because my index is 2. So 2 2's right here, 2 5's right here, 2 m's right here, 2 m's right here, and that's all the pairs that I have. So this 2 gets to come out as 1 2. This pair of 5's gets to come out as 1 5, and we're always multiplying these together on the outside. This set of m's gets to come out as one set of m's, one set of m. These sets of m's get to come out as another m. And the 2 and the n don't have any partners, so they don't get to come out. 2n. And then I simplify this by multiplying these together. 2 times 5 is 10 m n times the square root of 2n. Okay, questions I hope will get answered on these. I'd like for you to try C and D and see what you can do, and then we'll come back and give you the answers to those. We'll work them out together in class. So you try those and then come back to part 2 of this video.